Okay, now we're going to move on to a slightly more complicated, but actually only slightly more complicated version of those kinematic equations we just saw. And that is what we're going to call projectile motion, which is the motion of an object in 2 dimensions. Now this is the most complicated it's going to get, and honestly, for many students, this is going to be the most difficult thing that you learn in the entire module. Now, I don't mean that to say that it's going to be difficult. I mean that to say that this is about as bad as it's going to get. So if you are finding yourself stuck and confused, that's fine. It's very common to be stuck and confused with projectile motion. The most important thing you can do is practice a lot of different questions, because there's only so many ways that this can go, right? Unlike me, in reality, you don't have a question that involves someone failing to catch their projectile. In physics, there's really only 3 ways that the projectile can move. But let's take a look at that. So we'll go on to our projectile motion case, right? Now, projectile motion is just 2 dimensions of 1-dimensional motion, okay? We're going to do motion in the horizontal direction, and we're going to do motion in the vertical direction, okay? Now, you might think, Tom, doesn't that make things much more complicated? Not so much, to be quite honest, okay? Because there are some special, I guess, rules or simplifications we get to make when we're considering projectile motion, okay? The first assumption is that there is no horizontal acceleration, all right? Even though in reality there's things like air resistance, in the physics of our ideal world, in the physics that we're going to be looking at here, we essentially are going to assume that the ball only has downwards acceleration, or the projectile only has downwards acceleration. What this means is that yes, we have to do 2 sets of equations, one for vertical and one for horizontal, but the horizontal set of equations is actually very simple. There's not too many terms because A is 0. That's our first idea, that the acceleration in the x direction equals 0. As an aside, notice how I put a little x underneath it, right? Because what we're going to be doing is separating our velocities, our speeds, our accelerations, into what we'd call the y-axis and the x-axis. So our y acceleration is going to be ay, our x acceleration is going to be ax, and ax equals 0. Just take this off. So probably going to do some jumping around later. Right? Now, the second beautiful assumption we get to make is, unless otherwise told, ay is equal to 9.8 down. Now, in this case, I've decided that up is positive, which means 9.8 down means minus 9.8, okay? Might not be the case for you. You might decide that up is negative, right? But 9.8 meters per second squared. And what that means is essentially it's acting only under gravity, okay? You don't know what a force is yet, but our assumption is that the only force acting on the object is gravity, the force of gravity. And we will discuss what gravity is as a force actually this week, I think, but not now. That's what's important. So, I'm going to splice in a demonstration here, right? But there's one cool little thing I want you to guess, right? We're going to take 2 balls. We're going to drop them at the same time. Why don't I take 2? I'm going to try and do it in this case, and then we're also going to do it with an actual demonstration, right? And I'll splice in the video here. But I've got 2 balls, okay? One of them and another one. And what I'm going to do is I'm going to toss one of them. I'll toss this one, right? And I'm going to drop this one. Make sure I don't drop it on things. And they're going to be released at the exact same time. They have the same vertical behaviors. They have the same vertical distance to travel, even though they're not the same height, but ignore that, right? And they're going to be released from the same vertical height. They're going to be released at the same time, and they're going to be released with the same initial vertical velocity of 0. The only difference is this tennis ball is going to have some horizontal velocity at the same time, okay? So which one's going to hit the ground first? 1, 2, 3. I don't know if you heard that, or you can play it back, but they hit the ground at almost the exact same time. We'll do it one more time. Volume warning. That was loud. Or maybe I'll put, I've got something soft. No. Okay, cool. I'm going to do it again. Ready? 1, 2, 3. Right? and they hit the ground at the exact same time. Or more specifically, they hit the table at the exact same time. Why is that, right? In fact, they were even different shapes, right? Different densities, different masses, and also one of them had some horizontal velocity and one of them did not. And the reason why they they hit the ground at the same time, of course they released at the same time because I did it, but the reason they hit the ground at the same time is because of this principle we call orthogonality, okay? The x and the y axis are completely separate, right? It's like two of these vectors. Pick any two, right? Do you remember, by the way, vectors, remember when we decompose vectors into two dimensions? We're going to do that again, right? Any two directions, trying to make it front on is a bit difficult. Any two directions here ignore each other, right? Any motion that happens in the horizontal direction is completely irrelevant to the motion that happens in the vertical direction, okay? They are completely orthogonal. They do not care about each other. And that means that when we had those two balls, right, they had different horizontal characteristics. One of them was going no horizontal, it was only going down, and one of them was being thrown off to the side. But they had the same vertical initial velocity of 0, they had the same vertical height to travel, and therefore they fall the same distance, they take the same time, they hit the ground at the same time. You can watch the video back and prove that I'm right. Now, what does this mean? This means that we deal with two separate sets of equations. It's just like when we had our vectors that was in 2 dimensions and we just made it two one-dimensional vectors. You remember when we did the vector splitting? It's a similar vibe here. We're just going to have two different directions. We're going to have x and we're going to have y. And the principal difference between them is that the acceleration in the x direction is 0. Which means we get a special set of equations. We get only these two. That the velocity in the x direction is constant. Vx equals ux. There is no time factor there. The horizontal velocity is always constant for a projectile motion, and that the horizontal distance is simply the horizontal velocity, which could be written as u or v because it's the same, it never changes, multiplied by the time taken, right? That's it. And then our vertical direction is the equations you've done before. It's v equals u plus at. There should be an ay there. That should be ay. I'm a bad person. This thing has no fine control, like me. Sy equals uy plus half at squared. That went over 2, but that's fine. And v squared equals u squared plus 2as. The y-axis motion is the stuff you've already done. You know how to do this. And the x-axis motion is just easier. The only thing that makes this slightly more complicated is the fact that the two motions share the same time. All right? T is the same. What this means is that the horizontal and vertical motion start at the same time and they end at the same time. And what that actually means is you can use details about the vertical motion to infer how far it goes horizontally, right? If I throw a ball and ask you how far does it go, the first thing you calculate is how long it takes to hit the ground, and then you calculate how far it will have gone in that time, right? So this orthogonality. Now, the thing that is going to make you good at projectile motion is practice, 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 practice. I'm going to go over a few questions together, but to really, really nail it, you're going to have to practice a lot. The fortunate part is that there is no trick question. You can't get trick questions in projectile motion because it's always a parabola. It's always the same sort of stuff, right? I can try and make a hard question. I won't, but I could try. And even then, all it would do is take you a little bit longer to solve. Maybe you have to solve for more than one thing. Right? Maybe you have to solve for time, then you solve for distance, or something like that. That's all we could do. Let's try one. Let's try the one I just talked about, right? We've got a ball, and it's going to have an initial horizontal velocity, right? Notice how in the picture here, we've got the initial velocity pointing horizontal, right? I didn't say it in the question, but I said it in the diagram, right? We've got an initial horizontal velocity of 10 meters per second squared, and the ball is launched from a height of 150 meters. We are asked how far does the ball travel? So we're looking for this range. We're looking for this range of the ball. Okay? Now, how do we solve a problem like this? Remember our problem-solving strategy. We're going to read the question, we're going to identify all the relevant components, all the relevant values, then we're going to select some equations, and then we're going to solve them. So let's write out every single thing that could possibly exist. Treat this like a Sudoku, right? You're going to have some numbers, and then you're going to solve for some more numbers, and then eventually you'll have solved for the number that you want. So let's try the x-axis. All right, we have ux, that's easy, that's 10. Now it's in the positive direction, okay? We've got vx, that's the same thing. It's also 10 because it has to be. We don't know what the horizontal distance is. The distance traveled horizontally, we do not know. We would like to know, that's our goal. Our y-axis, we have our acceleration, negative 9.8. How do I know? Because positive is up, and so our direction is down, therefore our direction is negative. Our initial y velocity is 0. How do we know? We can look at it, right? We notice that the initial velocity is only horizontal. There's no vertical initial velocity, so the initial velocity y is 0. We do not know the final velocity, which would be the velocity when this thing lands. We've not yet figured that out. We do know the distance that the object is going to travel in the y-axis, right? We've got t equals 0 as well. We know sy, right? It's how far vertically is this thing going to go. And I've told you the cliff is 150 meters high. So you must think, yes, Tom, the distance is 150 meters. No, bestie. It's minus 150 meters. Why? Because the ball goes down. And down is negative. You must make sure you are keeping your signs correct. Ball go down, down is negative, therefore S is negative, right? Negative 150. Spooky, I know, that's vectors for you. Okay, we've laid out our mise en place as it was, and now we're going to cook up a solution. Get it? I was watching a lot of chef videos on YouTube. So, we want to find the distance traveled, Sx, right? So we go back to our formula sheets. Whoop, wrong way. Over here. We go, all right, Sx equals uxt. That's our formula. So Sx equals uxt. We go, all right, I know ux, don't know t. So now we need to find t, right? So now we go back to our formula sheet and go, what formula has t in it that we could use? Right? Not this one, because that's the one we're about to use to find ux. We don't know. Sorry, to find sx, we don't know. We could do this one, but we don't know what vy is. So there's two unknowns in that equation. It's not going to work. This bottom one doesn't even have t in it. So it's not useful. So we're going to use this one. Use this middle one. Because there's only one unknown there. We know what sy is, we know what uy is, we know what ay is, we just don't know what t is. So let's go here. We're going to use sy is equal to uy t plus 1/2 ay t squared. And we know all the values, right? We'll start subbing them in before we rearrange. Minus 150 equals 0 score plus 0.5 times negative 9.8 times t squared. Now, if I had missed either one of the negatives there, we would get t having the square root of a negative number, which is cursed and not allowable, okay? So, make sure you get it right. Okay, so we'll evaluate that. We're going to have t is equal to the square root of 2 times 150 divided by 9.8, which is square root of 2 times 150 divided by 9.8, and that is 5.53 seconds. And then we can finally, we'll write it down. I don't know why I write t equals 0, 5.53 seconds. Sorry if you're watching this video and going, Tom, why'd you write t equals 0, you stupid? Well, I've corrected it now. Now we've got t, right? So now we have Sx is equal to 10 remember that was ux, multiplied by 5.53, and that's 55.3. That's it. It goes 55.3 meters. Okay. So that's an example of our first type of projectile motion. Okay? The first kind of examination of projectile motion is the easiest one. It's the one where the object starts from horizontal rest and goes. Let's look at another one. And I went the wrong way, this way, right? A full parabola. I caught it, don't worry, right? So we want a case where the ball goes up and the ball goes back down, okay? And we want to figure out how high the ball ends up going and how far the ball travels. Now this looks complicated, right? And it is, but don't worry, it's going to be the last one we do today, right? And to do this, we're going to have to strategically think about things, okay? We are first going to divide this parabola in two. The beauty of a parabola like this is that it is symmetrical, okay? So let's divide our parabola in two, and we're just going to consider the first half, okay? Where the ball goes up and reaches the apex of its parabola, okay? Now, when we're considering this half only, we're going to split up, well, we're going to start to record all the values that we know, okay? So first things first, let's record our x values. Ux, we don't know. Sx, we don't know. Okay, so far so not good. Y. Ay, yep, that's minus 9.8. Dope. Sy, we don't know, but that's what we're looking for. Uy, we don't know. Not yet, we're going to figure it out. Vy, do we know that? T equals, we don't know that either. Okay, not looking good, right? But this is where physics comes in. This is where your understanding of reality comes in. First things first, let's notice, recalling from last lesson, we have a lovely little vector here. We actually know the initial velocity, just not in the x and y components. So we could separate this out into its horizontal and its vertical components. So let's do that. We've got a lovely little vector like this. That was 30 degrees. 30? Lord, it really doesn't like me writing up high up here. Anyway, 30 degrees and 23 meters per second. Lol. And so this bottom component, if you remember, is 23 cos 30, and this upper component is 23 sine 30. Right? That's the initial velocity in the y direction. This is the initial velocity in the x direction. We may as well calculate those. 23 sine of 30 is 11.5. So let's write that down in here, 11.5, and that's positive because it's up, okay? And we've also got our x, delete, cos 19.9. Okay, so that's over here, 19.9, that's positive as well. More items, but this is still not enough to solve for the vertical distance, sy, right? We still need some more information. We don't know what it is yet. There is one more piece of information we can glean from the question, and that is we have chosen the midpoint, right? The point at the peak of the trajectory. And at the peak of the trajectory, the vertical velocity is 0, because that's when the ball is in the middle of going up and starts to come down, right? If you throw a ball and look at it just as it reaches its apex, you'll notice that its velocity is 0 just at the top, or that its, vertical velocity is 0, right? Horizontal velocity may not be 0. And what this means is that our final velocity for the move we are considering, which I will remind you is just half of the parabola, right? But our vertical velocity, our final vertical velocity for that move is 0. And now the stage is set for us to solve, right? So notice there was a lot of setup here. There was a lot of getting the pieces and putting them in order before we begin, okay? Now, you will ideally be able to do this faster, but for now, slowly is more than fine. Okay, so we've got Vy equals 0. Now we can solve. We're trying to solve for the height, and we're also trying to solve for the distance traveled horizontally, but we'll consider that later. Okay, so to solve for the height, right, we have acceleration, we have initial velocity and final velocity. So let's look at our formula sheet. Whoop, wrong way. I'll rub everything out. We're going to use this equation here, right? It has everything we need but one. So we're going to use Vy squared equals Uy squared plus Ay Sy times 2. Yes, I forgot the 2, but I put it in the end, so that's fine. Now, let's sub in our numbers to start to solve. We've got 0 is equal to 11.5 squared plus negative 9.8 times Sy times 2. Now, importantly, if we'd gotten the sign wrong here, this would cause us some issues. But we didn't get the sign wrong, so Sy is equal to 11.5 squared divided by 9.8 times 2. And that is 6.74 meters. That's not nearly as high as I would have liked. Sad. Oh well. I guess 6 meters high is all right. Right? 6 meters high. Trying to like imagine throwing a ball. See how high it goes. That's fine. Anyway. So 6.74 meters is the height that it makes, so we can record that here. 6.74 meters. And so now we may move on to the second question. How far does it go? Right? How far does it travel horizontally? And you might think to yourself, okay, am I going to have to do a whole new set of equations? No. Let's keep it at the half, because we know that if we can figure out this distance, we just need to double it for the whole trajectory because it's symmetrical, right? These are the tricks that we want to be using. So, our initial x velocity, another little goof. I don't know why I wrote it in the S position, but it should have been in the U position. This is why you come to the live lectures, because then you can correct me in real time, right? We don't know what S is. So, we want to solve for S, x, and that's going to be equal to uxt. That's the only way to get it, equal to uxt. We don't know what we know what ux is, but we don't know what t is. So we've got to find t again. And we're going to use the same method as last time, or a different method. Doesn't matter this time. We've got every single y directional variable, so we can use whatever method we want. Let's use, just for, switching it up, let's use Vy equals Uy plus Ayt. That sounds fun, okay? Which means that 0 is equal to 11.5 plus negative 9.8 times t. So t is equal to 11.5 over 9.8, which is 1.17 seconds. We've got 1.17 seconds. Okay, so now we know that our initial and constant horizontal velocity was 19.9 meters per second. Our time is 1.17, and our distance traveled for this first half is 23.2. Wow, slay, very cool. Now we need to double that for our actual question, right? It's asked us how far the ball completely travels. So we'll double it and get 46.4. So 46.4 meters is our total travel distance. Now, these were just two worked examples, right? There are a lot of different examples of how to do these questions. The best thing to do is come along to the problem-solving workshops where we go through how to do these sorts of questions, right? Come along to them, come take a look at them. The week 2 one is going to be on projectile motion. I know this because I'm writing them and I'm deciding it's on projectile motion. So please come along, please enjoy the projectile motion, and I'll see you in the next video.